Welcome to this session on multimodals part 2. Again, my name is Manish Gupta and I work as a principal applied scientist at Microsoft. In part 1, I talked about multimodal encoders, right? So models which can basically process information expressed in multimodal ways. For example, image information, text information, video information, and so on, right? In this session, I'm going to talk about text generation with multimodal inputs. So notice that, of course, multimodal models are also used these days for image generation, video generation, and even multimodal output generation. But in this particular session, I'm going to only focus on problems where the inputs are multimodal in nature, but outputs are text only. Okay. So let me get started by actually talking about a large number of use cases where multimodal inputs lead to text output generation, right? And then we will actually spend the remaining half of the session in terms of various popular models to be able to achieve such tasks. Of course, one of the most popular tasks is image captioning. Given an image, basically, come up with a good text caption for it, and an extension to videos as well. Given a video, come up with a good caption for it. However, there are other interesting multimodal tasks. For example, visual conversation. So all of these snapshots, by the way, and task descriptions are taken from some papers which are referenced right at the bottom, right? So for example, in the visual conversation task, the idea is that you essentially provide the model with a particular image, like you see here, explain and also provide some text associated with it, explain the advantages of the product, right? And the model can actually come up with really good advantages of this car. So, but this is just factual kind of a conversation. Now, you could also have some interesting, common sense kind of conversation. For example, what are shown in the photo. Now, in the photo, of course, you see a very funny picture where a man is being chased by a chicken. Now, that's interesting, but the model anyway comes up with a man and a chicken. Now, you can basically say, what does the man feel and why? The user can say so, and then the model can actually infer he's scared of the chicken because it is flying at him, right? So there are very interesting such use cases where you can have visual conversation across various domains. For example, humor as well. So is this photo unusual? And this is clearly an unusual house. So it basically says, yes, it's a house that looks like it's upside down. How could someone get out of the house? And then it can basically say it has a slide on the side of the house using which somebody could potentially get out of the house. So it's not like it's just encoded world knowledge, but it also knows how to reason given new situations in those senses. Now, these multimodal chatbots may not really be chatting in short utterances. So, as you see here, this particular model could actually lead to much longer utterances as well. So given this image, a user could ask, what are things I should be cautious about when I visit here? And this multimodal chatbot can actually give very, very detailed, different perspectives of what one should be cautious about. And it can also help write a long travel blog post about trip to this place and so on. So these chatbots, visual conversations may be really long conversations as well, not just in terms of the length in the number of utterances, but the size of each utterance as well. These chatbots could also be used, these multimodal kind of models could also be used for doing scene understanding. So given this scene, somebody could ask, hey, what could have happened based on the current scene? And clearly, the information about what could have happened is not directly into the scene, but it is obvious that even a human could actually look at the scene and then say that some natural tragedy has happened here, for example, a hurricane or a severe weather event, right? And the model can actually rightly predict that. But it could also basically do knowledge grounded image description. So for example, if you ask introduce me this painting in detail, it's not just going to say that, hey, it's a girl painting or something like that. It's basically going to really nicely say that it's a young girl with a pearl earring, and this painting is actually very popular, known as the girl with the pearl earring. And it was basically painted by some Dutch painter in some time and in some year and so on. Okay, so it basically has very interesting information about historical facts and can correlate them nicely to be able to answer these questions. Well, yet another very interesting task in multimodal domain is visual question answering, where the idea is that you basically get an image as input and also a question associated with the image, and the model is supposed to come up with a very good answer. Here are some answers, generated by popular multimodal models like LLaVA, GPT-4, BLIP-2, Open Flamingo, and so on. Now, of course, we'll talk about some of these models in detail, but the idea is that, as you can see, even images which are sort of odd in nature, not really usual, right? So, for example, usually you don't see somebody sitting at the back of a van or a minivan and ironing clothes, right? So basically, even unusual pictures can be described really nicely by these kinds of models. Or look at this another example where there is a interesting meme. So the text and the image is part of the single input, right? And the model is asked, can you explain this meme in detail? And various models, based on their capabilities, can nicely explain what's going on in this meme. So it's basically chicken nuggets kept in the form of a world map, and therefore it's funny and so on. Okay, it can explain jokes. Right? Now, you see, so far we basically looked at image inputs. These models can actually also deal with audio-visual inputs. So although you may not be able to hear the sound here, but the idea is that you can imagine what kind of a sound this guy must be making, and what kind of a sound could be heard thanks to the dog outside, right? So essentially, but if the model is asked, hey, describe what you hear, and the model nicely says, I hear sounds of footsteps on the floor in the background, and there's also a dog barking in the house. Okay. It can actually figure out the audio and then relate that audio with a description in the text. Does the man wear glasses? And actually, if you notice, basically, yes, he wears a pair of glasses in the video. So, different lighting conditions along with what's going on in the video, it can nicely infer those things. Okay. Another one is basically on the right side, where this guy basically just gave a performance. So how was the audience's response? You can ask, and the model basically nicely says the audience was really enthusiastic and clapped loudly. Of course, you can't hear the claps in the audio, but when you have the slides, you can actually play this and hear the claps as well. Okay. What is this man doing? Well, the man is playing a saxophone on stage at the concert. So basically, the instrument is basically visible here, and essentially that's what the man was doing. Right. So essentially, these models are pretty awesome because they can actually describe videos also. Now, besides just holding dialogues with the users, they can also hold dialogues in a very interesting manner, in a knowledge-grounded manner, so as to seem like a very knowledgeable friend. Okay. So, for example, given this image, you could, as a user, you could ask, do you know who the man on the right is? Now, this happens so many times with us, right? Somebody talks about a movie and we have lost complete context because we have not seen the movie or we have forgotten the movie, right? But the interesting part is the models basically have a lot of world knowledge based on which they can actually answer these questions really well. The man on the right is Jon Snow, played by Kit Harington in the television series Game of Thrones, who is the lady on the left, and can nicely describe the lady as well. What is the relationship between them? It can nicely basically describe the relationship and also relate it with when did they meet and the 8th season and 7th season and all those interesting details. Okay. It of course also knows about landmarks. So for example, you can talk about what is this building. It can nicely tell that it is the US Capitol in Washington, DC. Okay. Lastly, it can also, these models are also very nice in terms of capturing dynamics. So for example, you could say, describe this video and look at the detail in which the video is being described by the model. It basically does not just say, hey, it's a young red-haired woman, big deal, but it also nicely tells many other details like striped shirt, posing for the camera, gray background, holding her fingers up to her mouth as if trying to be quiet and, describing the lips and the hair and the skin and everything. Trying to signal something and so on. So extremely deep details, as one can observe, right? As a human, one can observe. On the right side, of course, you see this video, and of course, you can summarize the video, sort of generating a video caption. But you can also ask factual questions like what direction the ship is going. And as you notice, the model rightly describes that the ship is actually moving towards the right side of the video. Okay. Well, there are many other use cases. For example, given a picture, can you write a story around this image for my child? So can be very much used for generating storybooks, right? So, and essentially, here's an extremely interesting story. You can pause the video and read it, or you can actually look at the paper and read the full story if you really want to, right? Look at this image and can you write me a master rap song around it? So, well, it can actually generate nice rap songs also. Given these visuals from a comic, can you basically tell me who the people in the comic are? It can really nicely tell you who are these comic characters. And this is not a popular comic. It's basically some not so, some sort of a offbeat comic in that senses, but still it can really nicely describe that comic. Okay. So all in all, what I showed you through these various examples are multiple multimodal use cases. That is, use cases where input is a combination of text, image, video, audio, and output is basically text. Several times just describing what was going on in the multimodal input, multiple times, answering questions, several times holding interesting conversations with users, and so on. Now, and of course, given that the models can do these tasks so well, newer and newer use cases are coming up. Okay, so I leave it to you to actually find many more use cases and read many more papers which can talk about several of these use cases. Okay. Now, what I will do in the remaining part of this session is to basically talk about different models, starting from a really, really basic one, which came up around 2020, 2021, about 2021, right, about 3 years back in time, all the way to some of the latest models. Okay, we'll try to understand how these models are able to basically generate text given multimodal inputs. Okay, the first model I'm going to talk about is called Frozen. Okay, so this model is nicely called Frozen for a very interesting thing, which you will understand very soon. Okay. Now remember, if there are multimodal inputs, just like in the previous session where I talked about multimodal encoders, you must have multimodal encoders in this case as well. Okay. However, in the previous session, I just talked about the classification tasks, and they just required encoding. Here you have to basically generate text as well, and therefore you would also need to augment these multimodal encoders with a text decoder. Okay. So on this slide, what you see is the Frozen's architecture. Okay, so let me actually partition the slide. The left part of the slide is basically about the training part of Frozen. The right part of the slide is about test part. Okay, so what you see on the left side. So how is Frozen trained, right? So the way the Frozen model is trained, let's just look at the architecture very quickly. So the architecture, of course, input is multimodal in nature. Here it is more like you're trying to do captioning. Most of these models clearly, just like multimodal encoders, are also trained using caption data, image caption data. Okay. So basically you have an image of a boat, and then you have basically this interesting caption, a small red boat on the water. And what you want to do is you see the user just inputs a small red boat, and you basically want to generate on the water. Or, basically you just want to generate the entire caption. Now, clearly at train time, you have both the text and both the caption and the image, and you want to basically use the language model, the large language model, to generate the tokens in the caption in an autoregressive manner. Okay, so now to process the image, there is a vision encoder. To process the text, there is a language model, basically, which is a text encoder. And then there are these self-attention layers which process the multimodal input, tokens coming from the image and tokens coming from the text. Okay. So from an architecture perspective, this architecture is pretty usual in that senses, given that you've already seen how multimodal encoders encode text. This is sort of a very similar architecture. Okay. For the vision encoder, you could basically use any of your VIT-based models, so vision transform-based models, or you could potentially also use ResNet kind of models. Okay, convolutional neural networks, that is, right? For language encoder, of course, you could use the BERT kind of models. And then when it comes to the final decoder guy, of course, you need to use some sort of a language decoder and something that generates stuff in an autoregressive manner. Now, the reason why this model is called Frozen is that the large language model, both the text encoder as well as the decoder, are kept frozen in nature while training this model on image caption data. Okay. So when you do fine tuning, with image caption data, you only fine tune the vision encoder. And that is why this guy is called Frozen. You keep the text part and the text encoder and the text generator frozen in nature. Okay. So the gradients through a frozen large language models, self-attention layers are used to train the vision encoder. The gradients, of course, flow through this, as you can see using those red symbols, right, red arrows. But then the weights are only updated for the vision encoder. Okay. Now, training is done using only image caption data, in the sense a pair of image and text associated with it. But at test time, interestingly, you could basically use Frozen in an in-context learning kind of a setup, such that you could do 0-shot learning, 1-shot, or few shot. Okay. Now, although the model is trained only for image captioning, the authors actually also showed that you could use it for question answering as well, visual question answering, that is. Okay. So for example, you could basically give this image as input and ask a question, what color is the car? And then it can generate an answer like blue, right? But you could also improve the accuracy by doing one-shot visual question answering. So you could basically give this image and then ask a question and provide the answer as well there, right? Who invented this? And you can say the Wright brothers. Okay, the answer also is supplied. It's an example for the model to learn that given the image and this question, this is the answer that the model must generate. Okay. And then of course you can basically give your test example image along with the question and with a prompt a colon such that the model basically generates the answer Steve Jobs rightly. Okay. And of course, in context learning, people have seen that greater the number of examples that you supply at test time, the better the accuracy. This is what they observed as well. And therefore, they also experimented with like multiple short examples, also called as few shot learning. Okay. Now, one important thing to notice is that this model can be used in an interleaved image text manner. The idea being that your input could have multiple images and it could have multiple text pieces as well. And then you could generate outputs, okay, and generate text output. Imagine doing a conversation on WhatsApp with your friend, where your friend basically posts some image, asks, and you guys discuss something, and then you post some another image, and you basically want to type the next utterance, okay. Now, in that case, your conversation may have multiple images and text pieces, text utterances interleaved with each other. And the frozen model is a very, very suitable model for doing these interleaved text image kind of processing. Okay. So that's frozen. Now, let me actually start talking about another model. And this time, let me talk about this model called Flamingo. Flamingo is not very old. It was presented at NeurIPS in 2022. Okay. And what you see on the left side is the Flamingo's architecture. Okay. As usual, you would always expect some image encoder, some text encoder, and then a text generator, right? A text decoder. Okay. That is what you observe here as well. But the architecture is a little more complex. Okay. So there is, there could be multiple images in Flamingo as well. So you basically, and it can also take interleaved visual text data. Okay. So for example, if there are two images, well, the two images are passed through the same vision encoder, which is basically pre-trained and frozen. So remember, unlike frozen, where the large language model is frozen, in Flamingo, the vision encoder is frozen. In fact, not just the vision encoder. Well, I'll talk about other things that are also frozen. So, on the text decoder side, but let's do it step by step. Okay. So vision encoder is frozen, and they basically use pre-trained ResNet as the vision encoder. So basically, they believe in convolution neural networks, and therefore they use pre-trained ResNet as the vision encoder. Okay. In fact, depending on the size of these vision encoders and the text encoder and the text decoders that you have, basically you would observe that Flamingo is available in 3 different sizes: 3 billion, 9 billion, 80 billion. Well, there is Open Flamingo as well, right? Open Flamingo models also available on Hugging Face. Okay. So the overall architecture, the idea is that if the input basically has input looks like this, there is an image, and then there is this text. This is a very cute dog, and then you have a cat picture, and then you want to generate you want to generate the completion. Of course, the golden completion, a very serious cat. Okay. So you have two images. The images basically go via the vision encoder, frozen pre-trained ResNets, right? And then basically they're processed using something called the perceiver resampler. Now I'll talk about the perceiver resampler on the next slide. So hold on, think about it like as a module, which basically gives you some further encodings, fixed size encodings from your images. Okay. On the right side, what do you see? So on the right side, basically, these are all images encoded. Now on the right side, you basically see that there is only a transformer decoder. So there's no text encoder separately as such in this model. Okay. So what do you have? You have a transformer decoder where basically you have the processed text. Now what is processed about this processed text? You took the input text, you basically deleted the image from there and replaced it with the image token, a special image token. You kept the text as it is. Okay. You again replace the second image with the image token, and you keep the text as it is. Okay. Now, when you basically process this this text, this processed text, basically you give it as input to multiple layers of a transformer decoder. Okay, multiple layers of a transformer decoder. Okay, this transformer decoder basically has, of course, multiple language modeling blocks. So, and the detail is basically what you see on the right side. Okay, the detail you see on the right side. So you can observe that it is basically using the inputs coming from the image side, visual inputs for cross attention. So that's the X is basically image inputs, visual inputs. The Y thing is basically the text inputs. And the first layer is basically the gated cross attention dense layer. Okay, a gated cross attention layer along with the dense layer. And then there is a typical language model layer. So let's look into the details on further on the right side. Okay. So the cross attention works as usual. Basically, if you remember, the self attention, of course, have QKBs coming from the same input. But in cross attention, you basically use the language side input, called as Y here, to supply the query. Okay. The visual input basically gives you the keys and the values. And those are the ones that basically are fed as QKVs to your cross attention sublayer. Of course, you have residual connections around them, and you have basically the feed forward, position-wise feed forward layer with residual connections as well. Further, after this, basically you have the typical, transformer decoder layer, which is basically, self-attention followed by another feed forward layer. Okay. So that's the architecture of Flamingo model. Now, of course, the only thing that is left to understand in this architecture is how do these perceiver resamplers work, which I will basically describe on the next slide. Okay. But another interesting thing to notice is that at a given text token, the model attends to the visual tokens of the image that appeared just before. So remember that. So you see, in an autoregressive sense, you would basically want this text to be attending to this image, to this text, and everything before that, right? But remember, the way the attention masks are defined in Flamingo is that the model does not attend to every image in the past, but only attends to the image just before this particular text, these particular text tokens. Okay, the nearest image. Okay. Now, Flamingo, of course, depends on pre-trained models, but then these pre-trained models are fine-tuned using a large amount of data. So more details about these data sets are in the paper, but the data sets basically include multimodal massive web, the M3W data set, which basically comprises of interleaved image and text pairs. Okay. It also basically is trained on image and text and video and text pairs, as present in these data sets, aligned data set, LTIP long text and image pairs dataset, VTP video and text pairs dataset. Okay. So this image on the left is the same as on the previous slide. But as I promised, now I'm going to go into details about the perceiver resampler. What does this guy do? Okay. So this guy basically, can actually process multiple images. So here there are two images, as you see. You could basically also provide video, by the way, right? So whichever way, so whether your conversation has multiple images or it has a video, you basically take those frames and you provide them as inputs here. Okay. So the vision encoder is basically taking those frames, and taking all of those three inputs. These three inputs, as I mentioned, could be like frames of a video or three different images in your conversation. Okay. Position signals are also added, indicating the sequence in which the images appear. Okay. After and of course, the vision encoder essentially gives you, if it is a VIT based encoder, of course, it gives you tokens. So the image is basically divided into multiple tiles. For each tile, you have tokens, as we discussed in the previous session. Okay, so you get those tokens. And then you flatten those tokens. So essentially, of course, you have these multiple tokens. You just organize them in a one-dimensional manner. So you just keep one after the other. And that basically gives you your XF. So remember, what is your XF? So essentially, if you have three images and you have like 9 tokens coming from each of those images, you basically have like 27 different tokens representing the visual input, the overall visual input across multiple images. Okay. Now, the idea is that you may have variable number of images, right? But what you want is a fixed size output. For example, a 32 sized output, 32 tokens only. Okay. Now, to be able to get a fixed size output, you basically use this perceiver resampler. Okay. What this guy does is a very simple thing. Okay. You essentially, on the right side, what you see is learned latent queries. Now, what does this mean? This basically means, if you basically wanted a 32 sized output, you basically have 32 embeddings, 32 vectors, okay, on the right side. They are like latent queries, okay? So, and we can call them as X, okay? We call them as X. They're randomly initialized and they're going to be trained over time, okay? They're randomly initialized, but they're going to be trained over time. Now, you see, and then the way perceiver resampler works is there are multiple layers of cross attention actually in this perceiver resampler guy. Okay, so you basically have XF and you have X. XF, remember, representing the current images in that senses. X representing the learned latent queries in that senses. Okay, You basically use X as the queries, and XF and X concatenated as keys and values. You compute, self-attention. And as far as I remember, this is complete self-attention. This is not autoregress. This is not mass self-attention. So you compute complete self-attention, and then you do feed-forward computation. And if you started with 32 latent queries, you will basically get a 32 sized output. Now that's basically super important because that ensures that you have a 32 sized output coming in from the overall images, that you basically pass in as input to to this model. Okay, that's how Pursuer resampler works, and that's how overall Flamingo works. Okay. So that's Flamingo. Now let's switch gears to yet another model, and this time it's the BLIP model. Okay, BLIP became actually very, very popular. So it also came up in 2022, and it's a ICML paper. I'll spend some time talking about how BLIP works. Okay, and as you will see, BLIP basically is a very interesting model because it sort of just builds on the advances in multimodal encoding. Okay. So of course, basically it's going to be visual language pre-training. And the nice part about BLIP is that you could use it for both as a multimodal encoder for image and video understanding, but you could also use it for generation. Okay, so models earlier before this have either focused on understanding or generation, but BLIP was one of those first few models to do both of them. Okay, BLIP has been trained on small hand-labeled datasets like COCO. Or rather, previous models were just trained on very, very small hand-labeled datasets like COCO or noisy datasets like Common Crawl. But BLIP was actually trained on a very, very rigorous cleaning pipeline. Again, I'm not going to talk about that rigorous cleaning pipeline in this session. If you want to read about that, you can read in the paper. But they have a very, very interesting pipeline using which they have cleaned the data across multiple iterations and ensured that the pre-training has been done on super awesome, super clean and super clean data. Okay. So let's look at the architecture for BLIP model. That's a very interesting architecture. You basically take an image, divide it into different tiles, just like you would do in a typical vision transformer kind of a model. Okay, as you can, BLIP's architecture can actually be described as a multimodal mixture of encoder decoder. Okay, multimodal mixture of encoder decoder. As you see, there are like these 4 towers, and I'll explain, of course, what these 4 towers do. But it's a multimodal mixture of encoder decoder. Okay. It comprises of these 4 things as you see them, right? Basically, the 4 things are unimodal image encoder. So this is the unimodal image encoder. Okay, unimodal text encoder. It's a BERT base in case of BLIP. Okay, so and a vision encoder is basically VIT base or VITL, and basically they believe in 16 cross 16 pixel images as tiles. Okay, so that's that. The third module is image grounded text encoder, and the 4th one is image grounded text decoder. So basically, you see, if you want to do multimodal understanding, this is the guy you are looking at, third guy, right? And if you want to do multimodal input based generation, the 4th guy is what you're looking at. Okay. So more or less, you might have sort of broadly understood now how this thing works, but let me go into details now. So this is the image. You basically divide into 16 pixel cross 16 pixel tiles. You pass them as input to a VIT model, and the VIT model basically, of course, is basically a standard transformer encoder model. So it has self-attention, it has feed forward. It basically gives you an encoding for the entire image. Okay, you have those encoding image tokens. Now, basically, much of this model has been trained on image and text, image and caption data. So here is the caption: a little girl holding a kitten next to a blue fence. Okay. So you take the text data, prepend it with a CLS token, pass it through the text encoder. So text encoder is basically a bidirectional self-attention, the usual one with residual connections, add and normalize and so on. There's no cross attention here. Basically, it's just a feed forward, another feed forward sublayer, position with feed forward, standard transformer encoder. Okay, n layers of vision encoder as well. Okay, and the 2 basically are pre-trained together using this image text contrastive loss, much like the CLIP model. Okay, much like the CLIP model, in a batch of n sample, let's call it B samples, right? In a batch of B text image samples, you would have B cross B pairs, and there would be, only B of those aligned pairs versus B square minus B are non-aligned pairs. You basically want to maximize the similarity of those B pairs and minimize the similarity of those B square minus B pairs. So the same image text, contrastive learning. Okay. Now, once you've done that, you basically have very good image embeddings coming from here. So that's the image embeddings. And notice that these image embeddings are going to be used for further computation. Okay, so for further computation, these image embeddings are going further computation. Okay. Now, the image grounded text encoder basically takes the same text, but with a special extra token added in the beginning called encode, a special token sort of randomly initialized, learned over backpropagation. Okay. This guy basically is like a standard text encoder, except that it also has a cross encoder, a cross attention module. So cross attention sublayer, right? So it has a bidirectional self-attention feed forward as well, but there's in between a cross attention sublayer, which basically takes these image inputs for cross attention purposes. Okay, and then it is basically pre-trained using this image text matching loss. Now, very interesting loss. Again, the way you would basically enable this loss is by providing matching text and image pairs and mismatching text and image pairs, and all that this the encode tokens representation needs to do is to basically predict whether this predict a 0 or a 1, 0 for mismatching and 1 for matching image text pairs. Okay. The last module is, of course, the language model. So essentially, it's a causal, it's a decoder. So therefore, it's an image grounded causal text decoder. So it has a causal self-attention sublayer, and of course, a feed-forward sublayer as well with a cross-attention. And as you can imagine, the cross-attention guy basically just takes the image input for cross-attention, and the text input basically goes through the entire model. Information fusion between the text and the image happens so as to generate awesome captions. Okay, so that's how basically the BLIP model works. But when it came to BLIP-2, which came in 2023, BLIP-2 is like V2 of BLIP. Basically, these guys also realized that this Q-former guy, this perceiver resampler kind of a technique, it's a little different technique. It's not same as perceiver resampler, right? But there's an interesting technique which basically helps you get really good results, get better results. Okay, so therefore they also use this Q-former technique, and we'll understand what this Q-former technique means. But one thing to notice is that BLIP and BLIP-2 are actually pretty different architectures. Okay, so now let me talk about how does BLIP-2 architecture look like broadly, and then we'll go into details on the next slide. So as you can see, BLIP-2 architecture basically also enables both the things. You can basically do vision and language representation learning, and you could use it for encoding purposes, right, or classification purposes. But you also have a vision to language generative learning. So you could basically also generate interesting answers or captions or utterances in the multimodal dialogue and so on. Okay. The first one, you could basically say, it's basically bootstrapping the pre-trained image model. So there's an image encoder and so on. And the second phase basically tries to bootstrap pre-trained large language models. Okay. So there are two phases in which the pre-training of this BLIP-2 model is going to be done. But overall, you see the BLIP-2 model is going to support our standard multimodal generative use cases, given this image and given a piece of text from the user, write a romantic message that goes along with this photo. The model is able to generate text like "love is like a sunset." It's hard to see it coming, but when it does, it's so beautiful, and so on, right? So it generates an interesting message around that. Okay. Now, as I said, the BLIP-2 model is pre-trained in 2 stages. The first stage basically tries to pre-train the first box. So vision language representation learning stage with a frozen image encoder. The image encoder is frozen in this stage. Okay. The second stage is for the second box, vision to language generative learning stage with a frozen large language model. Okay. Now, and the interesting thing in the first stage is basically this Q-former guy, which basically takes the text. Of course, the image input goes to the image encoder, but it also takes as input these extra bunch of queries. And these queries, you might actually relate them to the perceiver resampler queries, just like perceiver resampler would take a fixed set of query latent vectors. This guy is also going to do the same. It's going to take a bunch of, query latent vectors, query latent vectors. But unlike the perceiver resampler, which is basically only used to come up with the representation for the image, this guy is also going to take the text part. Okay, so it's basically going to be computing revised latent representations of those queries, but in a text-sensitive manner. Okay, So we'll basically look at details on the next slide. In fact, the Q-former inside itself, because it has to process images and text by itself, it actually has an image transformer and a text transformer inside itself. Okay, and that leads me to this diagram, right? To this architecture. From the previous slide, Q-former is a combination of an image transformer and a text transformer. Okay. So you basically take the input image, you pass through the image encoder. This image encoder can be a standard VIT or whatever, right? So you basically divide the image into different parts and pass it through a standard VIT. You basically get get a representation, get these latent vectors from the input image, right? Using those VIT or clip kind of models. Okay. Now this entire yellow box is basically the Q-former guy. Okay. So as I promised, it basically has two parts: an image transformer and a text transformer. This guy is image transformer. This guy is text transformer. Okay. So as you see, this image transformer has three different sublayers: self-attention, cross-attention, and feed-forward. Okay. As input, this image transformer basically takes learned query vectors. Now, again, this is a fixed size of query vectors. Let's say 32, is standard size, but you could also do with like 10 query vectors and so on. Okay. The image encoder is basically giving out these outputs, image representations, which are basically used for cross-attention. They are basically fed as input to the cross-attention, not to every layer, but to every other block. And that's basically pretty standard. I mean, typically when you do cross-attention, it's sort of standard that you do it every other block. Okay, so that's that. So that's that. Now, on the right side, you see basically the text. And here you have the standard text encoder, the standard transformer encoder. Okay, it has self-attention and it has feed forward. Okay, but there are like differences in the way these self-attention layers work. Okay, it's actually very fancy how these self-attention layers work across these image and text transformers. Okay, these self-attention layers basically tie the two together in fancy ways, and I'm going to talk about those fancy ways on the right side in the slide. Okay, the two are of course trained together. And the two are trained together, so it's basically meaning the entire of Q-former is trained together, using these three different pre-training losses: the image text matching loss, the image text contrastive learning loss, and image grounded text generation loss. The three losses are sort of self-descriptive in nature. I don't think I need to describe again, but just for the sake of completeness, right? Image text matching is going to basically just say if this image and text basically match with each other or not, binary classification. Image text contrastive learning is the clip style contrastive learning, right? Given this image and positive and negative text pairs, compute. So the similarity between positive pairs should be higher than similarity between negative pairs. That's the idea, right? You could have negative text pieces or negative image pieces, whichever. Okay. Image grounded text generation is basically going to generate caption tokens, and basically based on matching with the ground truth caption tokens, there's going to be a cross entropy loss, which is going to be backpropagated, right? So that's basically your three loss functions. But what is really interesting is the way this self-attention mechanism works, in the face of these three loss functions. Okay. The queries you see, which are there on the image transformer side, they can interact with each other. Okay. Of course, the queries can interact with each other because of the self-attention guy, but they can optionally also interact with the text through these self-attention layers. You see, this is a nice information propagation, which is also happening between the text and the image transformer via these self-attention layers. Okay. The image features are frozen and they are passed through the cross attention, which we already talked about. But let's see how this fancy attention masking is going on between the text and the image transformers. Okay, so and this self attention differs based on the loss function that you are computing. Okay, so the masks differ depending on the loss function. So this is for image text matching, this is for image grounded text generation, and this is for image text contrastive learning. Okay. Now, of course, the white thing basically means is unmasked. Okay. So now when you're doing image text matching, the interesting part is that all queries, of course, attend onto all queries, but they also attend onto text tokens. Okay. So it's like complete bidirectional self-attention across query and text pairs. It's basically like you concatenated text and image, and you basically are doing complete self-attention. Okay. But it's not just basically that you do complete self-attention in the input layer, but you do across all of those n different layers in both the transformers. Okay. So both the transformers are really connected in that senses. Of course, their feed forwards being separated out and completely different with their own weights, not shared at all, and so on. Okay. So bidirectional self-attention mask is basically what is used for image text matching. For image grounded text generation, as you would imagine, the text is going to be, since it's generating stuff, it's not going to be bidirectional. It's of course going to be autoregressive in nature. But every text token basically attends to every query token also. Okay, so it's basically like every text token can attend to previous text tokens or all the query tokens. Okay, that's basically that. Now the third one is image text contrastive learning, and there the obvious part is that text tokens attend to query tokens attend, essentially, and query tokens attend to the text tokens. Okay. Sorry. So in the image text contrastive learning, the image text contrastive learning, the idea is to be able to, of course, train both of the towers independently. So the query tokens only attend to themselves, right? Unlike what I said a little while back, the query tokens just attend to themselves and the text tokens just attend to themselves, text tokens only. Okay, that's how you get the two towers. And at the end, you basically compute the image text contrastive loss. Okay, so that's a fancy way in which the Q-former guy is trained. Of course, that's the first phase of training where you basically just train the Q-former weights with a frozen image encoder. And the second phase, of course, you're going to basically do the large language model pre-training. Now, how do you use this guy? So, well, essentially, you basically take the input image, you pass through the image encoder, you have the latent learned queries, you pass through the Q-former. By the way, the Q-former's output does not really output text tokens at all. It basically just output these learned queries. The learned queries basically get outputted to the LLM decoder. So if you basically just wanted to use the LLM decoder, you were, and in their case, they basically also use OPT model. For the decoder-based LLMs. Okay. So the way you would do this, you take the learned latent queries, you connect via a fully connected layer, and give it as input to the LLM decoder guy. Okay. But sometimes you also want to process text as input. So for example, in visual question answering kind of scenarios, you also have extra text which you want to provide. So in which case, what you could do is to do the same thing on the on the input side. You basically get the learned queries, connect with a fully connected layer, pass those queries. They are now in the LLM space. You can also provide the text and give it all as a part of the LLM encoder, and then basically use the decoders just to start decoding and generate the outputs. So, for the pre-trained image encoder, they basically experimented with VIT models, large models, and huge models from CLIP and from EVA CLIP. Okay, and they also for the frozen language models, basically they used OPT for decoder-based models, FLAN-T5 for encoder-decoder LLMs. The pre-training has been done on data sets similar to BLIP. So remember the cleaning pipeline, rigorous cleaning pipeline. They use those data sets. Plus they use 129 million images from COCO, Visual Genome, CC3M, CC12M, and SBU, right? Very large data sets in that sense. And 115 million images from the Lion 400 million data set. Okay, so the pre-trained very, very rigorously in that senses, and no wonder that leads to super awesome accuracies using BLIP-2. Okay. Now, next, let me talk about the mPLUG model. mPLUG model, again, is a 2022 model. As I talk about mPLUG model, I must also now tell you that people started not just fine-tuning these models, but also instruction tuning these models. So now the models that I'm going to talk about are trained on instruction-based image-text pairs. Okay. So basically, there is going to be an instruction with an image, what to do with the image. Okay, and in this league, I'm going to talk about various kinds of models. We start with mPLUG, but here I'm also going to talk about LLaVA and MiniGPT4. Okay, so that's that. You see, the architecture is what you see on the right side. So essentially, there's a visual encoder which takes the image, where there's a text encoder, and then there's a text decoder. Okay. For the text encoder, essentially you use 6 layers of the BERT base. The remaining 6 layers are what you see here. This part that is in orange is actually called as the cross-modal skip connected network. I'll talk about this. Of course, you can see the architecture here, and you can sort of make sense out of it yourself. But it's a 6-layer BERT base which is used for the text part. That's what it is practically. Okay. On the right-hand side, you basically see the standard transformer decoder with all the 3 sublayers, the causal, self-attention, cross-attention, and feed-forward, and that's basically a 12-layer transformer decoder model. Okay. For the visual encoder, basically this guy, they basically use a clip VIT model, clip base or clip large, VIT base or VIT large model. Okay. So that's that. Now, the only thing that is left for me to explain here is basically what is this cross-modal skip connected network, right? So this is an interesting network, okay? I mean, in some ways, it is not very different from what we have learned so far. Basically, you process the image via visual encoder. You process the text using a text encoder, which is a 6-layer BERT base, first 6 layers of the BERT base. When you get these representations from the image side and the text side, you basically use the asymmetric co-attention in that sense is where you basically use the image side so as to basically supply cross attention. Okay, queries are from the text, keys and values from the image side, right? Whatever outputs you get from here, you basically combine with the image outputs, image encodings, right? And you essentially do the standard transformer encoder self-attention and feed forward. Okay. Now, among these 6-layer stuff, as far as I remember, they basically do 2 layers of this asymmetric co-attention and 1 layer of this full self-attention, and then they repeat the entire thing 2 times, and that basically leads to the 6 layers of pre-trained from the BERT base. Okay, so that's basically the mPLUG model. It's a pretty simple model in that perspective. And of course, the outputs coming from the mPLUG encoder are actually fed into the cross-attention module, cross-attention sublayer, so as to start generating outputs from the LLM decoder. Okay. Now, of course, it is pre-trained using these 4 different loss functions. So the first one is the image text contrastive loss, image text matching loss, which we understand by now anyway, right? And it's basically also pre-trained using the masked language modeling. So on the text side, you could be masking a few things and expecting the model to generate those text pieces. So that's also there. And lastly, basically, of course, you have to have a generative prefix LM loss, the autoregressive loss in that sense. Okay. So that's about the pre-training. Now, of course, the last thing that is left is pre-training data. So they basically pre-train using 14 million images and text from MS COCO, the image text pair, visual genome, conceptual captions, 12 million, and SPU captions. So the standard data sets which have been used to pre-train other multimodal generative models as well. Okay, so that's mPLUG. Now let's talk about LLaVA. Okay, so LLaVA became super popular in recent times. In fact, LLaVA has multiple versions. The latest one is LLaVA 1 Vision, and I'm not going to talk too much details about LLaVA 1 Vision. The architecture doesn't change too much. It's just that the model is trained much more rigorously. Okay, let's just talk about LLaVA by itself. Okay, so LLaVA by itself, came up in 2023. LLaVA the architecture is as follows. You basically take an image, pass it through a vision encoder, and then you learn a projection layer so that you can project these image embeddings onto the text space, the LLM text space, both in terms of the space itself, the encoding space, right? And the second in terms of the size of the dimension, so dimensionality itself. Okay, both of those basically are transformed using this using this projector in that sense, or a transcoder in some ways, right? And then you also have, if you have the text piece, some text associated with the image as part of input, you basically also concatenate it and give it to the large language model, and the large language model generates a response. So the architecture is super simple in that sense. Okay. You use the COCO image captioning data and for training this model, for pre-training this model, and you essentially use the language only GPT-4. So now that's the awesome part. I mean, you're using GPT-4, which is really a very expensive and a heavy model, and therefore it knows how to generate the output nicely. Okay. So basically, the model is trained using 158K language image instruction following samples. Remember, all of these basically mPLUG, LLaVA, mini GPT-4, they have been, of course, trained using the standard image text captions and image text data sets, but they've also been instruction tuned later using some instruction tuning data, which is specifically made available. Okay. So for example, in LLaVA, they especially created these 158K language image instruction following samples, which are obtained from 58K conversations, or rather, which contain 58K conversational data, 23K detailed descriptions of images, and 77K complex reasoning complex reasoning given the image kind of a data. Okay. So all of these data sets, by the way, have been generated using GPT-4 itself. So all of them have been generated using few-shot prompting to GPT-4. Okay. Obviously the image-based GPT-4 in that sense, right? But then the large language model they use is just the text-based GPT-4. Okay. So the pre-training is done in 2 stages for this model. So first it is pre-trained for feature alignment, and the second stage is to pre-train it end-to-end. I mean, or other, you can call it fine-tuning end-to-end, stage 2. So the first stage is really pre-training, second stage is fine-tuning in that senses. Okay. So the first stage basically involves taking the conceptual captions CC3 million data, and they take the data set and filter out 595K image text pairs from there, and they use it for pre-training. They also pre-train using the conversational data. You see these 58K conversations, they use that also for pre-training. Okay. In this pre-training stage, the visual encoder and the LLM weights are frozen, and only the projector is basically what is pre-trained. That's basically the one that is learned. Okay. Of course, the loss basically is defined over answer tokens. So whatever answers are generated, you basically compute the loss over them, backpropagate, learn the projector by keeping the large language model and the vision encoder frozen. In stage 2, you basically, you keep the visual encoder frozen, weights frozen, but update both the pre-trained weights of the projection layer and the large language model. So the vision encoder is basically kept as it is, but then, in the second stage of fine tuning, you also fine tune the large language model weights. Okay. And then the fine tuning is actually done on the entire 158K instruction tuning data. The data is generated using GPT-4, but the model, of course, basically GPT-4 is not publicly available. So the model actually that is used is LLaMA. So essentially it combines the vision encoder that is used is the pre-trained clip vision encoder. So basically you use the VIT large vision encoder, and then you combine with the LLaMA, large language model. And then do the training in 2 stages, the pre-training stage and the fine-tuning stage. Okay. Now, while doing this, of course, you also give language instruction, some sort of a system message to tell the model what to do. Okay. Essentially, when it is conversational data, this is a system message that you can provide, a chat between a curious human and an artificial intelligence assistant. The assistant gives helpful, detailed, and polite answers to the human's questions. Okay. So although the model has not been specially instruction tuned for safety and so on, but the assumption is that since you ask the model to be polite, it will basically give polite, helpful, and safe answers in that sense. Okay. So that's that. So the system message. So basically, the inputs that go into the large language model is templatized as follows. You basically give the system message. You basically then give a special token, stop token, and a new line. And then you say the human says something, that the instruction, right? And then the assistant says something, and then the human says something, and then the assistant says something. This particular stuff, X1 instruct, X2 instruct that you see there. Now, it could be either text and image or image and text, depending on, these LLaVA models have been trained using data sets with one image. So the first one could be basically sometimes you keep the text, first and then the image, and sometimes you keep the text, keep the image first and then the text. Okay, it could be either. So LLaVA model has not been pre-trained using data with multiple interleaved images and so on. Okay, that's that. And of course, therefore, for the remaining utterances, the remaining terms, of course, you just pass the text and you append that particular thing. So that's how you basically give it a full conversation as input, and you basically ask the model to generate the assistant replies, essentially. Right? That's the LLaVA model. Let me quickly talk about Video-LLaMA, and then next I'm going to talk about mini GPT-4 and call it done in that senses for this session. Okay, so Video-LLaMA. Now, Video-LLaMA, of course, basically is a model which can actually process video. So you basically take an input video, you pass the video frames to a visual encoder, a VIT, and a Q-former combination. So the VIT model takes each of those frames, comes up with some representations, and you basically give it to a Q-former model, and the Q-former comes up with a limited number of queries in that sense, right? So the video Q-former aggregates the frame level representations and shares the same architecture with query transformer, the Q-former that we saw in the BLIP-2 case. Okay. The audio encoder basically, takes those audio segments, creates the audio spectrogram out of it. Now, you see, what is audio? Audio basically comprises of frequency and wavelength and so on, right? Magnitude at different frequencies and so on. So all of that can be represented using a nice image called as a spectrogram. And there are many pre-processing libraries like PyAudio and Audacity, which can give you a spectrogram given a particular audio sample. Okay, so you take those spectrograms and then basically give it to an audio encoder. Okay, and this audio encoder essentially just uses, basically this is just the same as audio spectrogram transformer from ImageBind, and you take both of these representations. And here is a representation coming for every image frame, and here is a representation coming for every audio segment in that senses. Okay, you combine them with the positional information and give it to video queue former. This is the queue former place, right? So essentially video queue former and audio queue former, such that at the end of it, you basically get exactly the same number of queries from both the sides. And then what you do is to basically do linear transformation, so as to bring them both the video part and the audio part in the same as the text space. And then you can basically combine with the text instructions, like a human says something, and then you can put up the video and the audio information, describe this video. And in their case, they use Vicuna or Llama as the LLM, so as to basically then generate awesome captions for this video. Okay. So you could think about this kind of a model as if it basically provides video and audio soft prompts along with the text prompt to the LLM, so as to generate awesome captions. Okay. As you notice, this guy is basically the multi-branch cross-modal training part of Video-LLaMA architecture. There's a vision language part on the left side, and then there's an audio language branch on the right side. Vision language part, of course, needs to be pre-trained. So it's pre-trained using video caption data set with 2 million, which has video clips to text generation task, right? And also on the image caption data. So it's basically trained both using image text pairs and video text pairs. Okay. So the way the fine-tuning is done using video-based conversational data. So there are two phases for the vision language branch. The first phase basically does the pre-training using video text and image text data, caption data typically. But the fine-tuning is actually done using video-based conversational data for visual instruction tuning. Okay. And the data basically comes from several sources, 3 different sources, but details you can again read in the paper. Okay. The audio part basically is pre-trained using audio text data, so audio related components on a audio caption data. So you have the audio caption data, which is used to pre-train the audio language branch. Okay. Lastly, let me talk about this third instruction tuning model called MiniGPT-4, instruction tuning based multimodal model called MiniGPT-4. The architecture actually, honestly, is very, very similar to the previous 2 architectures that we talked about, the LLaVA and the Video-LLaMA models. And in fact, it's a simpler architecture, if you ask me, really, right? So it basically has the LLM Vicuna, which takes #human as the input, and also it takes whatever images or video you provide, it basically processes them through a VIT and a QFormer setup, does a projection, linear layer projection, and also takes other text tokens so as to generate awesome captions. Okay. Just like the other 2 models, Video-LLaMA and the LLaVA model, it also aligns a frozen visual encoder with a frozen LLM, so as to with a projection layer, so as to generate good captions. The training is done in 2 phases, pre-training and fine-tuning. Pre-training phase, you basically keep the vision encoder and the LLM frozen, both the vision encoder and LLM, just like in the LLaVA pre-training, where you basically just pre-train the projection layer. Okay. But the pre-trained data is actually much more rigorous. You basically use a combination of image captioning data set from Lion, conceptual captions, and SPU. Okay. The fine-tuning part is also more rigorous compared to the LLaVA framework, where you fine-tune using instruction tuning data, 3,500 specially curated detailed image description pairs. And the input format I already talked about. You basically give it as #human, and then the image features, the IMG token, image features, end of IMG token, and the instruction, and then the instruction, the assistant instruction in that sense. Okay. An instruction, basically, they try with 2 different instructions for results that they show in the paper, like describe this image in detail, or could you describe the contents of the image, and so on. Yeah, and they show some awesome results in the paper. Some of the results I'm also showing here. In fact, many of these results that you see here are based on other kinds of models like GPT-4o. Not many details are known about the architecture, but I just also wanted to show you these models are so strong now that they can basically take these audio about, let's say, a meeting chat which is going on. So there's a meeting chat which is going on. Maybe you can hear, maybe you cannot. But the idea is that it's a meeting which is going on between 4 speakers. And the idea is to basically ask the model, hey, what's going on in this meeting? Okay. And the model nicely describes basically different people, because people refer to each other by their names, and that's how the model understands who are the people. There are 4 speakers in the audio, and Mark is saying something, and Nick is saying something, Dirk and Xavier are talking about something, and so on. And if you basically actually ask it, can you describe the transcript with speaker names? It can actually do that as well. This is exactly what these guys have been saying. Mark is saying good morning. It's the first team meeting. Team is saying morning. I mean, other people say morning, and then so it nicely attributes whatever pieces of text that was said or whatever pieces of speech that was said to the right speaker, right? Also called as the speaker derivation task. Okay. These models can also do really awesome, text generation on very long videos. So, for example, this is again a demo from GPT-4o, demo page. You can actually look at this demo on that link. Okay, so you can take a 45-minute, almost a 45-minute lecture video, and you can basically just tell the model, "Hey, summarize this for me." Now that's huge, right? 45 minutes is such a long video. But this model, GPT-4o, can very nicely summarize. In fact, it can actually create slides as well. So it can basically say, hey, there is a first slide introduction, challenges of optimizing LLMs, optimization flow, and it basically nicely gives you bullet points and sub-bullet points and so on. And it continues on the next slide. I basically also continued more description as you see it here. Okay. So very nice tools that are available for lecture summarization. In summary, in this session, I talked about many multimodal use cases where the input is multimodal inputs, where the inputs are multimodal in nature, but the generated text is generated output is text. Right? I broadly talked about models like Frozen. In fact, I tried to cover what has happened in the multimodal generative world in the past 4 years or so. I started with Frozen, then I went into Flamingo. We talked about BLIP and BLIP-2, right? We also talked about mPLUG, and rather basically these ones that we talked about, mPLUG, LLaVA, Video-LLaMA, Mini GPT-4, these are more instruction-tuned multimodal models. The first 4 are not really instruction-tuned. I mean, of course, the instruction-tuned models do better. But we understood detailed architecture of each of those models. Now, clearly, in this session, I did not talk about image generation or video generation, but that's something that you can learn about from other sources. Okay. Thanks for your attention. Happy to connect with you. Those are my coordinates. And if you want to learn more about these models or even image and video generation, that's my YouTube where you can listen to more such videos. Thanks so much, and now open to questions.